load controller in the last class, and before that we had discussion on the governors. So one more critical system which we'll briefly look at is the excitation control system. So as you might recall, and we had discussed earlier also regarding the excitation, so we'll just quickly overview that thing and then we'll move ahead. So as we understand that this, when we say excitation supply, that is basically the power supply for the your field circuit, which is located on the rotor. So as it says here, excitation systems can be defined as the system that provides field current to the rotor winding of a generator. Well-designed excitation systems provide reliability of operation, stability, and fast transient response. So all those things can be ensured if we have a proper excitation system, and also we understand that as the machine will actually operate and deliver power to the loads in a power grid, then as the loads fluctuate, then the loading with the change in loading, there is a good possibility that the voltage will also fluctuate, and that particular voltage now needs to be maintained within the stipulated limits, which are usually given by the electricity authority or the governing bodies which rules pertaining to electricity supply. So this exciter system, the excitation control, is very critical in terms of maintaining the voltage in the desirable range, and also because if you recall the phasor diagram which we discussed earlier, there was your V phi and you have EA, and accordingly your delta angle, that also determines how much, at what particular delta you are operating, how much will be the real power output and also the reactive power output. So those few things, and so especially the voltage control and the power factor control, those particular things can be achieved through the excitation system. So it is also very critical, and the basic thing we had discussed earlier also, this when we started the discussion on synchronous generators, we discussed this type of a brushless exciter, which is like the standard which is used. That so just to rewind this thing and help you recall what we discussed earlier was that here the synchronous machine is this one. So you have your main field winding on the rotor and the main armature winding on the stator. And from the stator main armature winding, as we know, we draw the three-phase output. So the thing is that now we want to supply, we need to supply a DC current to this main field winding so that the magnetic field is set up. So this type of arrangement, which we discussed earlier also, is done that you have a smaller AC generator which is placed with the opposite winding location. So for this smaller exciter generator, what we have is that we have the armature of the exciter on the rotor itself, and we have the field winding of this particular exciter on the stator. So the thing is that we basically want to avoid that slip ring type of arrangement, brushes and slip ring. So what will happen now is that now we can supply that DC current directly to the exciter field, which is on the stator and stationary, it's not moving. So we can directly supply it there, and now this will set up a magnetic field, and as the rotor rotates due to its magnetic the mechanical coupling with the shaft of the turbine, so what will happen is that this changing magnetic field will set up induced voltage and current in the exciter armature, and then because it's a three-phase AC generator typically, so we need a three-phase rectifier to convert it to DC and supply that DC current to the main field winding. So this is the overall schematic of the exciter which we discussed earlier also, but today we will look at this thing in somewhat more detail. So this is like the overall schematic, but then how do you control the excitation? So we are going to have few discussions of few systems which are used for controlling the excitation supply to the field winding. So there are 4 common excitation methods which we'll be looking shortly in brief, just an overview. So one is known as the shunt or self-excited machine. Then you have something known as the excitation boost system or EBS. There is also a possibility of a permanent magnet generator, which is nothing but, permanent magnet generator, as you will see, is same as what we discussed earlier as the brushless exciter with a pilot exciter, where there is no external supply needed, just the permanent magnets can generate the magnetic field. And then there is something with the auxiliary winding. So each of these methods has got some advantages and disadvantages, and we'll look at that. And all these methods, they will always use something known as an automatic voltage regulator, or AVR. So whenever you have, if you visit any particular power plant, you will see that this AVR is a very integral part of these power plants, in terms of the excitation supply. And what is this AVR? It is again basically an electronic circuit. So as it says here, an automatic voltage regulator, AVR, is an electronic device for automatically maintaining generator output terminal voltage at a set value under varying load and operating temperature. It controls output by sensing the voltage V out at a power generating coil and comparing it to a stable reference. The error signal is then adjusted to adjust an average value of the field current. So as you can understand, this is again that type of feedback type of mechanism. So here, like the governor was sensing the speed or the frequency, and based on that, it was giving an actuating signal for the motion of the guide vanes. So this is something similar, you can understand, but I mean, in terms of the control system, it is also a control system, but very different from governor. Here, as you can see, we are sensing the voltage, and you have a reference setting of the voltage, and if there is a fluctuation in the voltage due to the changes in the load or the load power factor, so accordingly an error signal is sent for adjusting the value of the field current. So field current is adjusted in such a way that your induced EMF or EA in the armature windings is adjusted, and ultimately the terminal voltage is adjusted and you get the desirable output. So the exciter rotor AC output is rectified to a DC input for the main generator rotor. So this is, I mean, nothing but this one, that the exciter armature output will be rectified for being fed to the main field as a DC input. So this is the basic principle. Any question on this? I think this we have already discussed in the beginning also. Anyone having any question or doubt on this thing?
No, sir.
Okay. Okay, so let's move ahead then. And now we'll look at these four mechanisms and how they differ, and they slightly differ from one from the other. And the idea is that we want to basically now control that how much how much supply will be coming to this exciter stator. So basically, as you can see, this exciter stator is receiving some supply, and accordingly, this supply will determine how much will the field winding, and that will determine what will be the voltage induced here, and hence the current flowing here, and that will ultimately determine that what will be the main field, your current in the main field, and the magnetic flux. So we will look at these few methods for controlling this low current input to your exciter field, which is on the stator. So the first method is known as the shunt or self-excited scheme. So in this one, as you see here, you have your main generator here. It is the rotor and the stator, and then you have the excitation system mounted here on the same shaft, as you can see. So as it says here, the shunt, and you have the AVR here, which is getting the supply from the stator itself. So as it says here, the shunt method features a simple and cost-effective design to provide input power to the AVR. This method requires no additional components or wiring. When problems arise, troubleshooting is simplified with less components and wiring to validate. So as you can see here, there are no extra components. The stator, whatever is the stator generated current, that is being fed to your AVR, and based on the control logic here, the voltage sensing thing here, and comparing it to the reference, it just gives the supply to the exciter stator. Okay, so the field of the exciter, which is on the stator. So it's a very simple scheme. There are no extra things here. So, and then the working here, as the generator is rotated, the stator supplies input voltage to the AVR. So that is obvious. We have discussed that. You are supplying the this thing. from the stator output, the AVR is being supplied. In addition, the AVR has sensors that monitor the output of the stator, and also you can have, for additional reliability, you can have additional sensors for monitoring the output of the sensor. The AVR supplies power to the exciter, and that is rectified to the DC current. So as we've been discussing, so the power which you supply from the AVR, you rectify it to a DC current and supply it to the exciter field. Okay. The current is induced onto the stator and load output, and then the machine operates as we have discussed. So this is the simplest scheme where there is no extra unit, no extra, anything extra is not here. Just the simple stator is voltage is given to the AVR, and that accordingly with the control mechanism here, it gives a suitable current supply to the exciter. Some drawbacks are there with the simple scheme. I mean, the advantage is that it's very simple in operation, and in terms of the complexity, it is low. But the biggest drawback to this system is that the AVR is impacted by the load the generator is powering. When the load increases, the voltage begins to decrease, and the AVR must provide more current to the exciter to support the demand. So that is one problem here, as you can see, that if your load is increasing abruptly, and then the voltage will tend to drop. So suddenly there is this extra supply which needs to go to the exciter circuit here, which this particular type of scheme might not be very suitable for supplying. So this pushes the AVR to its limits. If the AVR is pushed beyond its limits, the excitation field collapses. So especially if you have a severe voltage drop due to a very sudden load increase, then the requirement on the AVR for suddenly increasing its current output will be very severe, and that might lead to a collapse of the entire excitation field side. And if that collapses, then overall generator it collapses, and the operation comes to a standstill. So the output voltage is reduced to a small amount. Another thing is that if a short circuit occurs in the supply to the AVR, the generator will not have an excitation source. So that is also obvious. If there is a short circuit here, so then AVR is shunted out and nothing is being supplied to the exciter. So again, the machine operation will stop. So this causes a loss of generator power output. Generators with shunt or self-excited methods can be used on linear loads, which are usually constant loads. Applications that have non-linear loads, so varying, and especially if the variation is in a non-linear fashion, then it becomes really complex. These are not recommended for generators with this excitation method. Another thing is that the harmonics associated with non-linear loads can cause excitation field breakdowns. So it's a very simple scheme, and for simple loads which are constant or just varying in a small range in a linear fashion, this might work. But if you have some complex variation of the load, or if it is a non-linear load, then this type of scheme might not really be very suitable, because it doesn't have any extra source to back up the supply to the AVR, and for emergency conditions it might not function very well. So this is the first method, the shunt or the self-excited method. Then the next one is the excitation boost system. So as we understand, in the simple shunt or the self-excited method, the problem was that whenever there is a sudden load increase and the voltage is dropping very drastically, and so those emergency conditions, the AVR can't really drive the exciter current to a suitable limit, and it might lead to excitation field collapse. So we need to basically provide some sort of boost or some sort of support to the AVR for those emergency conditions. So that is being taken account here, and accordingly this second system is known as the excitation boost system. So this EBS or the excitation boost system comprises of the same basic components, supplying inputs to and receiving outputs from the AVR. But then along with those basic components, there are some additional components in the system, which are the excitation boost control module, which is known as the EBC, and one excitation boost generator. So you have another small generator here along with the exciter generator is definitely there, but along with that there is one extra excitation boost generator, which is controlled by a excitation boost control module. So this EBG or the excitation boost generator is mounted on the driven end of the alternator. Physical appearance is the same as a permanent magnet. The EBG supplies power to the controller as the generator shaft rotates. So if you see, this is the schematic here. So you have this extra the excitation boost generator on the same shaft, and a smaller generator before the exciter. One more is there, and you have the EBC controller and the EBC supply, which is driving the input to this EBC generator, and this EBC controller is receiving the control signal from the AVR. So as it says here, the EBC control module is connected in parallel to the AVR and the exciter. So you have the AVR and the exciter. This was the normal path. So as you can, if you compare it with the simple shunt type of exciter, if you see AVR and exciter, they are in one particular path. And here also that same path is existing from AVR supply is going to exciter. But in parallel, you have one additional path. And this additional one is that you have one EBG, excitation boost generator, which is controlled by this excitation boost controller, and which ultimately is controlled by the AVR control signal. Okay, so you have this excitation, this EBG and its EBC. This EBC and EBG, both of these are in parallel to the AVR and the exciter. So that's what it says here. The EBC control module is connected in parallel to the AVR and the exciter. The EBC receives signal from the AVR. When needed, the controller supplies varying levels of excitation current to the exciter at levels that depend on the needs of the system. So and what will happen in normal operation, it will be operating same as the basic your shunt or self-excited system. So under normal conditions, this AVR control signal going to the EBC controller will ideally be zero. There will be no excitation current going here, or the actuating signal will not be there. So this will ideally, in normal circumstances, this will not produce any extra current. But if suppose there is a sudden load increase and there is a sudden drop in the supply to the AVR, then that AVR control signal actuates this particular operation of the EBC boost controller and the excitation boost generator. So under those emergency circumstances, this AVR sends a control signal to the EBC controller, which activates the EBC supply to the excitation boost generator, and then that extra current needed for coming out of those emergency situations is generated by this excitation boost generator and supplied fed to the exciter here, which is on the same shaft. So that way, this system will have a capability to ride through the the extreme events or emergency situations where the voltage is dripping down suddenly. So the additional power feed to the excitation system supports the load requirements. This allows the generator to start and recover the excitation voltage. This excitation system is not recommended for continuous power applications. So as we discussed earlier also, that if you have a continuous type application, if it is just driving a steady load, a base load type of circumstance, then this simple system is good enough. But when you are expecting a lot of fluctuations in the load, then you need this type of additional support. So that's what it says here. It is not recommended for continuous power applications. It is intended for emergency or backup power applications. When the generator starts the EBS system, when the main generator starts, the EBS system is disengaged until operating speed is reached. The EBG is still generating power, but the controller does not route it. So obviously, because if this is having a permanent magnet type of arrangement, or even if it's electromagnet and having some residual magnetism and it is on the same shaft which is rotating, so there will be some power, maybe it will be generating, but it will not be routed to the exciter. Only in emergency conditions, when you have this AVR control signal coming, then this will be routed to the exciter. So this system allows for dynamic response. The dynamic response means, from electrical background, definitely people will understand. Others also can understand is that, dynamic response is that and there are transients when there is let's say there is a voltage drop. So how quickly does your system voltage rise and stabilize back to the actual value? So that type of dynamic response will improve with this excitation boost system. It is less expensive and meets requirements for providing 300% short circuit current. So such extreme requirements. So if there is a short circuit and 300% current is going 200% extra, 3 times the rated current. So obviously the voltage will drop in such circumstances. But up to that limit also, this can sustain and help the generator ride through those extreme situations. Non-linear loads such as motor starting are improved when compared to the shunt or self-excited method. So this is about the excitation boost system. So far?
No, sir, it's fine.
Okay. Okay, so let's go ahead. So these are the two systems we have discussed. One was the basic shunt system for continuous operating loads and steady state conditions where there are no emergency situations or fluctuations. And the second one, EBS type of system where you have this extra capability of supporting the main AVR and exciter supply under extreme conditions. So, and as we saw, it can supply, it can support in terms of the current rating. If it goes 3 times above the current rating, then also it can help the keep the voltage in the acceptable range, bring it back to the acceptable range. Now we'll look at two more options, which are like some other alternatives to these and which are useful for different purposes. This permanent magnetic generator or PMG is similar to what we discussed earlier, if you recall, was the pilot exciter, brushless excitation with a pilot exciter. That means there is no additional supply, no extra, external supply is needed, and only a permanent magnet is there. So here, as you can see, there is a permanent magnet generator PMG, which is on the same shaft as the main rotor and the exciter. So as it says here, generators equipped with permanent magnets are amongst the most well-known separately excited methods. And so this can also be classified, like a separately excited thing with a PMG. So the excitation current is given by supplied by this PMG type of thing. So PMG supplies isolated power to the AVR when the generator shaft rotates. The AVR utilizes the extra power when supplying nonlinear loads such as starting of motors. So you have, it's very similar, if you can see here, if you compare with this system, only difference is that here you have this excitation boost generator and it was being controlled by some control mechanism and only coming into picture under emergency conditions. Whereas this PMG will be continuously, it is always there. You don't have any extra controller, only the AVR can, control it directly. So, but this will be continuously in the operational mode. This will be generating. So whenever there is there is a non-linear load like starting of motors and all, this PMG can provide support. A clean, isolated, uninterrupted, and three-phase waveform is produced when the generator shaft is turning. So that is the advantages. I mean, the waveform is also very stable and good, and it can operate in the isolated mode also. It doesn't need any external supply. It can just operate on its own. So that is an advantage always, as we said, because if you see here there will be some external supply which will be needed for this type of generator. But in this case, there is no external supply needed at all. Just the permanent magnet generator is operating on its own. Some of the benefits of using generators equipped with the PMG excitation method are as follows: that the excitation field does not collapse, allowing for sustained short circuit faults to clear. So this the excitation field here it's continuously always there. The PMG generator is continuously generating. So even if there is a sustained short circuit fault, which is sustaining for some time, it can help the generator ride through this, provided that the circuit breaker is not tripping. I mean, it's not that severe, and the machine is under operation, but at a reduced voltage level, then this PMG can help in clearing the fault. Changing load does not impact the excitation field. So as you can see, the excitation field is mainly determined by the PMG. And because this, the magnetic field of this is constant, it's a permanent magnet. So any load changes and due to which there are voltage shifting, that does not affect the PMG output. So changing load is not impacted, is not impacting the excitation field. Voltage is created on initial startup and does not depend on remaining magnetism in the field. Another major, big advantage is that, as you can understand, that for a normal synchronous motor, a synchronous generator without this PMG, there is some residual magnetic field in the rotor, and as it rotates, this particular magnetic field builds up. But in this case, the permanent magnet is already having a high degree of magnetization, and it is so this thing can operate. The voltage build up does not start from a very small value. due to this already permanent magnet being there in the excitation side, the voltage can start from fairly high value, whereas for a typical rotor, this will be, the field will gradually build up as the motor catches speed and the thing sets up. So voltage is created on initial startup and does not depend on the residual magnetism in the rotor side. During motor startup, excitation field does not collapse because of lack of AVR supply. So, which was the disadvantage of the shunt type of thing, that if you have a sudden, due to heavy loads which are being suddenly put up and AVR was collapsing, that thing will not occur here because PMG is there to support. The PMG system adds weight and size to the generator end. So that obviously, because you are adding one more smaller generator here. It is the most commonly used excitation method for applications that use motors that start up and shut down and other nonlinear loads. So as you can understand that PMG and this EBS both are competing options for nonlinear loads. But if you compare amongst these two, like the first one was the simplest, that is for sure. But this, as we discussed, this simplest one is too naive to take care of any major load changes or nonlinear loads. So whenever you are having a fluctuating load or a nonlinear load having a lot of complex variations, then the first option is ruled out. But then these two options come in they are competing options. One is either the excitation boost system or another is the PMG type of mechanism. So as compared to excitation boost system, as you can understand, this is simpler because you already, you don't have that type of extra control mechanism and external supply which is needed. It's just a permanent magnet generator which can work in isolated mode also and without any need of extra control circuitry. So that's why it says here that it is the most commonly used excitation method for such applications where you have a lot of motor load coming up suddenly, or startup or shutdown of these motor loads, or non-linear pattern of variation of the loads. So PMG will be definitely more simpler and cost effective as well in terms of if you compare with the EBG type, EBS type of system. And then finally, the last one is the auxiliary winding. And this one here, if you see, is very similar to the first one, but there is some difference. So if you look at this particular thing, this figure, and if you look at this first figure, can you spot the difference? It is like one of those puzzles for kids of spotting the difference.
Sir, that additional winding coming from AVR from left side.
Yeah, yeah, we go to this one. Yeah, right, this one. So even if you look at the stator here, the cross section of the stator, interestingly, you will find there is this extra layer which has been shown here. For representation purpose. If you see here the stator, so you have this type of a representation, 3 layers primarily. And if you look at this one, here there is one extra layer in between, this brown one. Okay, so these stripes were there in the first one also, and then this dotted portion. But there is this extra brown layer here, which is basically one additional auxiliary winding. So this auxiliary winding is one additional winding which is coming up here. So as it says here, it's interesting. It's very simple. You can say a very simple modification, sort of, if you want to talk about in Indian terms, you can say it is like a jugaad for the traditional system. So what they are doing now with this auxiliary winding is that the auxiliary winding method is also, it's a very simple one because just a simple modification to the existing system, and has got different applications now. So this method has a separate excitation field. However, it does not use a component attached to the driven end of the shaft of the generator. So as you can see, there is no extra component here, neither the excitation boost generator nor the permanent magnet generator. Because those methods, obviously the cost will increase, the size of the machine will also increase. You have one extra generator coming here. So that's what it says here. This method is a separate excitation field. However, it does not use a component attached to the driven end of the shaft of the generator. These methods use shaft rotation and a permanent magnet or generator to supply the additional excitation. Those earlier methods, the EBS and the PMG. So here what we are having, here it says here, an additional single phase winding is installed into the stator itself. So this is the additional single phase winding. As the generator shaft rotates, the stator main winding supply voltage to the AVR as in all the above mentioned methods. So the basic operation in steady state is same. So when the generator starts operation, then as the shaft rotates, the main windings, the main stator winding, it will supply the voltage to the AVR. Then this additional single phase winding, what it will do is that the additional single phase winding supply voltage to the AVR. This creates the extra excitation voltage needed when supplying non-linear loads. So you have this additional extra single phase winding, which is not contributing anything per se to the power output of the machine, but its output is entirely being fed to the AVR. So when you are having normal operating conditions, then it's not an issue. Even if you draw some power from here or not, that is okay. But yeah, even if it is coming, no, that can be adjusted, taken care of with the control mechanism. But the extra advantage comes when there is a non-linear load and there is a sudden jump in the load, due to which due to that type of sudden loading condition, like heavy motor starting or those type of operations, the stator output, the three-phase winding output will dip suddenly. So the supply being fed to the AVR from this side dips. So in that case, this additional single-phase winding supply which is being given to the AVR, that comes as a support. So that way, that's what it says here. This creates the extra excitation voltage needed when supplying the non-linear loads. So you have some sort of support over and above the main stator field winding, which supplies the AVR under the non-linear conditions. So for linear load applications, so it's a very simple one as compared to if you see the more complex one, the most complex one is the EBS one, and then lesser complex is this PMG, and even less complex is the auxiliary winding. You don't have any extra thing on the shaft, just one extra auxiliary winding supplying the AVR. So if you compare these methods for linear load applications, shunt, EBS, PMG, and aux excitation methods, anything can be used for all these four if you have a linear load application. But for linear load application, shunt excitation is the most cost-effective method. So as we said earlier also, that if you have a constant type load or linearly varying load, then obviously this is the most cost-effective because it can deal with the load variations, and there is nothing extra, no additional system is there, so it is more simpler also and more cost-effective as well. But the choice comes when you have a non-linear load application. So whenever you have a non-linear type application where there are significant load shifts, load changes, or non-linear pattern of load variation, in that case the shunt excitation is ruled out. So then you have these three options: EBS, PMG, and aux. And as it says here, out of these three, conventionally PMG excitation has been the most common and the widely used. Because if you look at it, if you just compare these three, the EBS and the PMG and the aux. So as you can see, there is a trade-off. One is the complexity, another is the performance, two parameters. So in terms of complexity, this is the most complex one, and will provide the best performance because you have an additional controller and it's properly controlling the generator output of this EDG. So this will be the most complex one, but obviously performance is also best, but more complex and slightly higher on the cost side as well, and complexity as well. Whereas this is the simplest one amongst the non-linear methods, because there is no extra generator, but obviously the performance here won't be that good because there is just one additional single phase winding which is supplying the AVR, and also it is just like it is continuously operating. It is not that it is coming into picture only under emergency conditions. So performance, it is just like some additional support to the shunt method. So performance wise, not as good as EBS and PMG, but most cost effective, you can say, and least complex. And the PMG one is in between, you can say. It is like the optimum of both of these two. So in terms of complexity, it is less complex as compared to your EBS system, and in terms of performance, it is having a better performance than the auxiliary winding system. So that's why it says here the most popular method for dealing with nonlinear loads has been traditionally the PMG excitation method. So these are the four control methods for controlling the excitation supply. So any questions anyone is having, please feel free to ask. Or any discussion or anything related to this to ask.
Sir, I have a doubt regarding PMG type.
Hmm.
So, like in other two cases for non-linear, like I understood that how this varying current is supplied, but I couldn't understand that how in PMG it is supplied, because this permanent magnet will supply a constant current.
Correct. Correct.
Okay,
So
so then has exciter current to be controlled, like in
right,
time.
right. So basically, ultimately, what is happening is that your supply to the exciter needs to, you need to vary that thing. So
Hmm.
in this case, what is happening? You can look at it alternatively also, because the PMG will be continuously in operation. It's because
Hmm.
it's having a permanent magnet thing and on the same shaft which is rotating. So it will
Hmm.
provide continuous supply to this exciter. So in fact, here you can flip and look at it the other way also, that basically here the primary excitation is coming from the PMG itself, and now the stator supply becomes like a secondary thing.
Okay.
Okay.
Huh.
So even if the stator supply drops, there is not much effect because the primary supply is already there. Okay.
Yes. Yes.
So that way it's very stable, and that's why the earlier thing which we discussed. This was the one, the brushless exciter with
Hmm.
a
Pilot
primary
exciter.
pilot exciter. Yeah, that is the case.
Thank you, sir.
And anyone else? Any other question? So if there is nothing else, then we'll stop here today, because this is all for excitation control. So next thing, we'll start from the next class a new topic, which will be the power factor improvement methods. Because when you talk about the generation side, this power factor is a very critical thing, as we've been discussing also. And depending upon how much is the power factor of the system, the system, sometimes if the power factor is poor, you need to have much larger generation to supply the same real power. So there are some methods, because especially in the modern power systems, because in the recent times, as we see, there are several non-linear loads which have come into picture, which are non-linear and much more having much complex voltage current relationship. So traditional systems used to have just the your resistance type or the inductive type loads, R or RL loads, and it was fairly easy to analyze also. And in terms of power factor, there was not much variation. But nowadays we have a lot of electronic gadgets which are there. So all these, which is known as the IT load, information technology load. So all the computers, laptops, and even the CFLs and tube lights which we are having. All these things actually they are having a much complex relationship between voltage and current. Something different from the just simple Ohm's law. And ultimately, if you resolve that, you see that it has a bearing on the power factor as well. And there is a much stringent requirement in terms of the reactive power demand. That's why the reactive power demand has become very substantial these days, and it's a very crucial component of the supply. So, and some of the major blackouts which have occurred across the globe, many times in India also, and globally, the most famous one is the blackout in USA, because that was at a very big level, and because it happened in USA, so entire world took note. So that 2003 US blackout was like almost half of United States grid collapsed, the eastern half basically, and that was triggered basically due to this type of a voltage collapse due to the inadequate reactive power in the system. So what will happen is that because the reactive power is having a very close relationship with the voltage in the system. So if there is a reactive power demand and it is not supplied adequately, so that as the unmet reactive power goes on increasing, the voltage keeps on dropping down. So in fact, it takes the shape of a nose curve. So if the unmet reactive power demand, let's say I'm plotting the unmet reactive power demand on the x-axis and voltage on the y-axis, then as the unmet reactive power goes on increasing, the voltage will initially, it will have a droop type characteristic, it will keep coming down, but then at some point it just collapses. So it's also known as the nose curve, it has a profile like this, gradual droop and then sudden drop here. So that type of thing might occur if you are not supplying the reactive power demand in the system adequately. It can lead to a voltage collapse and the entire collapse of the grid. So that's why in the modern power systems, it's very important to supply the reactive power along with the active power. So from next class onwards, we will look at first, both the things. How do we analyze what is the power factor requirement, the reactive power requirement in terms of what is the power factor and how much it needs to be improved. And then we will do some sample calculations and all to see that in a given situation, how much power factor, to improve the power factor from a given X value to some better value, how much reactive power needs to be supplied and how that reactive power can be supplied. Okay, so that will be our next discussion, and for now we will end here. Any closing remarks or questions anymore? Okay, so we'll stop here.